So hello everyone, this is lecture 11 for the atomic physics. In the last lecture we were discussing the questions based on the spin orbit interaction, and today we will go back to what we were discussing, that is this energy shift in the splitting, means how they split. So we get this formula, that is ah squared divided by 2, and then we substitute the value for j, that is l plus half and l minus half, and we get for the different splitting, and that was given by this a by 2 l h square, that was the upshift, and the downshift was minus a by 2 l plus 1 h square, and the difference between this will give you the energy difference. This was al plus half h square. So you must remember these formulas. So we discussed these. Now we will see these shift in some other way. So what is this a h square? So we know the value of a, so we just substitute it here, the complete term. So you can see in the previous lecture we have the value of a, and this is h square. Now see, if you divide and multiply with the alpha square, then it will turn out to be that you will get the Rydberg constant and sc. So this is the simply value of that, and this will reduce to this. Now you will substitute this here to get the value of VSL for this. So we will get this VSL equal to, just substitute the in place of AH square, we will just substitute this value, it will be divided by 2, JJ plus 1 minus L plus 1 minus SS plus 1. Now again we will take the difference and find this difference. So how can we do that? So we know this whole thing will be equal to L for the JL plus half, and this whole thing will be minus L plus 1 for JL minus half. So just write it L here, and then write minus L plus 1, and then find the difference between those two. So that will give you this. That will be simply delta equal to R net SC, jet 4 alpha 4 n cube L plus 1. Now here you will see that this energy difference, we get this in some other form, that is depending on the LL plus 1. Means for the same atom, if you have the different levels or the different orbits, means SPDF, then that will give you, means it is inversely proportional. Means for P it will be, means P for it will be less, so this will be greater, difference will be greater, and for D, this L plus 1 will be larger, so this difference will be smaller. So that's how you can find for the different orbitals for the energy difference. And if it is for the same orbital like P for different atoms, so you can find that it is proportional to the Z to the 4. So those have the high atomic number, that will have the high energy difference. So that's how you can just consider this. Now see, this is not giving us the correct value, means the energies and the bands. So what was that? Because there is some relativistic terms also should be added, means this was the shift, but this was not the correct shift, means there was some other term should be added to get the correct values. That was a relativistic effect, that is quantum relativistic effect, we know. So we need to add this shift also into this to get the correct values. So let's see what is the relativistic effect in the quantum relativistic effect. So this is total energy given by kinetic energy plus potential energy. So in the relativistic regime, we know the kinetic energy is given by total energy minus the rest mass energy, that is P square C square plus M naught square C4 minus M naught C square, plus potential energy. Now take the M naught square C4 term common, so that will give you this 1 plus P square by M naught square C square, and this will be M naught C square outside the square root, minus M naught C square plus V. Now see, just to open this from the binomial expansion, and you will get M naught square 1 plus P square 2 M naught square minus 3, and the higher terms will be neglected. So this will be this. Now just multiply this term inside this, so it will be M naught square C square will cancel out, and this will give you P square by 2 M naught, and this term will remain, means this will give you M naught cube and C square. So this you will get. Now see, this is your total energy term again, this is the initial value, that is H naught Hamiltonian. Now this is the correction value, this is a relativistic correction term, so that's why we call it that. So this is the correction value. If the wave function associated with the hydrogen like atom for the unperturbed case is psi naught, then the energy eigenvalue will be H naught. But if it is perturbed, then we'll get this correction term, and we need to find the value of this. So from the quantum mechanics, how to find this correction energy term, that will be given by psi star, psi conjugate. Inside this you will write this whole value, that is minus will coming outside, and psi d tau. So after solving this, you can get the energy correction value. So I'm not going to the explanation, it is from the quantum mechanics, so you must remember this formula. So this will solve to this value, minus R infinity SC Z4 alpha square n cube 1 upon L plus half minus 3 by 4n. So this is your relativistic energy correction term, and now you must add it to the this one. So these two both will combine to give you the fine structure. So that's how we get the fine structure, means this is your total energy, means the initial energy, this was given by Bohr, then you will come out to be the spin orbit coupling, sorry, not coupling, it is the interaction simply, and then this relativistic energy term. So these two will combine to give the correct values, and we call them as a fine structure. So the two correction term, one for the relativistic mass change and the other for the spin orbit coupling, combined together to give the fine structure. So that's what I told you just. So we just write it this complete thing as delta E Fs. This is fine structure. So this will give you the correct energy value. This is depending on N, L and J in all the three. Previously it was depending on the N and L only, but now it is J factor is also included here. So let's see now what we are getting. This is your delta EFS will be given by, first you need to write this LS coupling term which we get here, and the second one is the relativistic term, that was this. Now we need to solve this, so just take this thing common, that is minus of this we take common, it will be 1 upon N plus half, and again from here this will be this divided by this, means just take this thing common and you will get this minus 3 by 4n. Now see, we need to solve this for two values, that is j equal to L plus half and j equal to L minus half. For j L plus half, this whole term will reduce to L, and for L minus half this will reduce to minus L plus 1. So just take this thing and solve this. So for first we will solve for j equal to L plus half, so it will be L here and L will cancel out, and you would need to try to solve this, and you will get delta EFS equal to this. So you will get this very easily, just try to solve. And now in place of L plus 1 we can write 1 as half plus half. So L plus half will give you j, so it will give you j plus half minus 3 by 4n. Now we will calculate for the L minus half. So delta EFS for L minus half. For L minus half, this whole term will reduce to minus L plus 1. So again you will get this as your solution. Now we can write it as L minus half plus half. So L minus half will give you j and it will give you j plus half. Now you will see that this expression is same as this. So now we have the common term for the delta EFS. And after seeing this we can see that it is not depending on L. So it is also not depending on L. So it is independent of L. Now its fine structure constant will be, means this fine structure term or the energy correction term will be independent of L. So that's how you need to remember this. So that's how it will distribute. So now the total, this ENLJ will given by En plus delta EFS. So in place of this we will write this correction term. This will be this. Now this is nothing but this is called the Dirac equation, you must remember this, and this is the complete formula. Now from this you can get the correct values of main spectrum or the wavelengths. Now this equation establishes that fine structure energy of H atom depends upon J value, not on L value. So if you have the same J value, that should have the same level of energy splitting. So let's see fine structure in the hydrogen atom, how it will be. So N equal to 1, we will have L equal to 0, that is S. And now for S it is 0, so J will be simply half. So this will be S half and there will be no splitting, so it will be simply 1. And now you know that J is given. So if J is there, then this fine structure constant must be there. So there will be some downshift, En minus that will give you downshift. So there will be this S downshift like this up to here. So it is not depending on L, it is depending on J, that's why there will be shift. Now for N equal to 2 you will have L as 0 and 1. For 0 it will be S, no splitting, and for 0 you will get 2S half term, and this will be downshift like this. Now for P it will be 1 by 2 and 3 by 2. So if J is same, then the shift will same. So that's why this 2P half and 2S half will have the same level, but this 3 by 2 will have the upper level. Now see, this energy difference is less as compared to this. So as J increases, this difference decreases. You can see from this equation, if J increases, the difference will decreases. That's why 3 by 2 will be here. Now for N equal to 3 you will have 0 1 2, and that is SPD. So again for S half, P half will have the same level, P3 by 2 and D3 by 2 will have the same level, and D5 by 2 have the upper level. So that's how 3S by 2 and P by 2 1 upon 2 have the same level, and 3 by 2 3 by 2 and 5 by 2 will have the upper level. So that's how they will split. And now from these we can get the different lines. Now see, they only get the 5 lines from these Dirac structure. We get only 5 lines for the H alpha transition. What is H alpha transition? That is to the Balmer series, is 3 to 2. So they get only the 5 lines, but in actual there was 7 lines. So later with the help of the Lamb shift, which we will discuss, you get all the 7 lines. But see, this was a very much explained term or the explanation for the lines. So how you can get that? Now see, this was the shift. For 1 it was become 1 as 1 half, and for 2 it was 2p3 by 2, means this is the same as we discussed here. So these are the same shift. Now how can we see that where we will get line and where we can't, means why this transition not from here to here but only possible for here to here? And there will be some rules. So those rules will be, We call them electron transition between these levels will be electron dipole transitions. So electron dipole transition, they will follow those rules. So what is the selection rules for that? Delta L can be only plus minus 1, means from D to S, that will be difference will be 2, so that is not possible. Difference can be only plus minus 1. That is, it is D to P only possible, not D to S. So and delta J must be 0 or plus minus 1. See, you can say that here D to P is possible because P is also there, but see, it is 5 by 2J and it is 1 upon 2J, so difference between J is 2. That's why this transition is not possible. So you must see all these rules to take the transitions, and J equal to 0 is not possible. So you must remember these three rules. These are the selection rules. So here, that's how you will get all these lines. From here to here is possible, here to here is possible, because this J is 0 and delta J is 0. Okay, and you can see D to P, that is delta L will be 1. So that's how you can see that, because both have the same level. So if any one is possible, so that line will be there. If both of them P2, when there will be some other term also, if both are possible, then you will get two lines from the same term. Means that's how you can just differentiate them. So you must remember these three rules. So according to these rules, we'll get only these 5 lines. So this is H alpha line, that is 3 to 2, we get 5 lines. But see, there was in actual there was 7 lines. So after introducing the lamp shift, we will get all the 7 lines. So we'll discuss in the next lecture the lamp shift. So later on, lamp shift was introduced, and with the help of lamp shift, all the 7 lines found. So we'll see in the next lecture how we get that. So that's all for today. Thank you everyone.